Вот это вперед, да? Мгм. Okay, I'm sorry. I'm sorry. I'm stuck. I'm really very happy to be in this audience again because for some last years I wasn't participating in this conference because my research wasn't related in any way to rare earth ions. But in old times, so to say, I was a constant participant of this conference, of this symposium. And actually, for the first time, I participated in this symposium in 1970, so 52 years ago. I don't think there is anyone else who participated at that symposium. So I am very happy that I returned back to this, so to say, rare earth activated community. Thank you very much. I came here with a topic which is absolutely new for rare earth for spectroscopy of rare earth activated ions. It's spin noise spectroscopy. It has never been used for, has never been applied to these systems. So, and I am sure that everyone here knows what is spin noise spectroscopy. So in the first part of my presentation, I will tell what is spin noise spectroscopy. Will describe the main characteristics, the main unique and very curious properties of this method, and then I will turn to rare earth ions and will tell how we managed to apply spin noise spectroscopy to this system, and will describe some unique and very curious features of this technique. So to start with, everyone knows what is magnetic resonance. If we have a spin in a magnetic field and we apply AC magnetic field with a frequency corresponding to spontaneous precession of this spin in magnetic field, we observe this the magnetic resonance effect. The question is, can we detect, can we measure the precession frequency without applying any alternating, any AC magnetic field to the system? The spin noise spectroscopy answers this positively, answers this question. That's exactly what spin noise spectroscopy does. It measures or detects precession, spin precession, without acting on spin with AC magnetic field. But I will start from afar, from many years ago when I worked in the laboratory of Petr Petrovich Feofilov under his supervision and was engaged in magneto-optics of rare earth activated crystals. He suggested, Petr Petrovich suggested that I should do this. And at that moment, I understood very simple things, that there is that Faraday rotation, or better to say, some contribution to Faraday rotation is proportional to magnetization of the spin system. So by measuring Faraday rotation, we can measure magnetization. And the question I asked was, what is the smallest changes in magnetization we can detect experimentally? Or in other words, what are the smallest rotation of polarization plane we can detect? Or what is the limiting polarimetric sensitivity of a polarimeter? And at that time, I worked at Vavilov State Optical Institute. There was a special department who were designed such polarimeters, and I knew that polarimeters of high class, the best polarimeter, the sensitivity of best polarimeters at that time, lay in the range of 10 to the minus 3 degree, 1,000th degree. It's, of course, it's a small angle, but what is it the limit or not? We, at that time, we worked in neighboring laboratories with Evgeny Borisovich Alexandrov, we discussed this problem and came to conclusion that the limiting polarimetric sensitivity should be at least 3 orders of magnitude higher. And actually, there was nothing special that should have been done to achieve this sensitivity. We should use, of course, we have to get rid of excess noise of the laser source. We should use laser or not laser, any light source with smallest excess noise, smallest excess fluctuations. And and it should be bright enough to have a large photocurrent, because then the short noise will be lost. It was clear for us that the only fundamental limit that restricts sensitivity of polarimetric measurements is short noise. And so the main thing that we use was a balance detector, which is shown here. It's a very simple thing, and now these balance detectors are produced commercially. It consists of a beam splitter. Of a beam splitter and 2 photodetectors. When this detector is in a balanced position, then the 2 photocurrents are subtracted in a differential circuit of this scheme. When intensity of in these 2 channels are the same, then it is 0 at the output, no matter whether intensity is greater or smaller. It means that intensity fluctuations are suppressed in this with this balance detector. But any rotation of polarization plane will cause disbalance in this detector, and the signal at the output appears. So it was a very simple scheme, and indeed we achieved the highest sensitivity which can be in principle achieved. It lay in the range of 10 to the minus 8 radians. Okay, I'm sorry. So the situation was very peculiar, I would say. I knew that Faraday rotation proper, Faraday rotation itself, or saturated Faraday rotation in usual sample, was around 1 radian. The smallest changes in Faraday rotation lay in the range of 10 to the minus 8. So it was a very small variations of Faraday rotation. So it's impossible that Faraday rotation will be stable to within 8 digits. So it was clear that we have to see it, have to discover some fluctuations. The more so that it was clear that these fluctuations should be present. Because we know that in magnetic field, paramagnet is magnetized along magnetic field, so there is no, the magnetization is aligned along the field. There is no transverse magnetization because all the directions in transverse plane are the same. But if we look at the tip of magnetization vector, we'll see that it should fluctuate both in length and in direction, because the spins in any paramagnet are constantly moving. How to make these measurements? There are 2 possible geometries. On the left is Faraday geometry. On the right is so-called Voigt geometry, when the light propagates across the magnetic field, and the right, this geometry is of the most interest for us, because if in this geometry there is no Faraday rotation, the constant Faraday rotation, since the light propagates across magnetic field. I'm sorry. But if any fluctuating magnetization arises on this picture on the right. I just see this. Then it will, this transverse fluctuating magnetization will process around magnetic field during the dephasing time, during the time T2, and then it will be replaced by another realization. And as a result, we'll obtain some, at the output of balance detector, we'll obtain some picture like shown here with some pronounced frequency, pronounced Larmor frequency, and the spectrum of this noise will be a peak centered at Larmor frequency with the width corresponding to the phasing time of the system, to the time T2. So it will be nothing else but magnetic resonance. So that was the idea of our experiments, and the only question was whether the sensitivity, polarimetric sensitivity will be enough to detect it. And we did this experiment with Evgeny Borisovich Alexandrov. As an object of study, we used sodium vapor, and the tunable dye laser was tuned close to the line of sodium, where the conversion of magnetization to Faraday rotation is the greatest, and sensitivity of the method it's the greatest, and we have managed to detect the signal, the magnetic resonance in the Faraday rotation noise spectrum with a signal-to-noise ratio of around 100. So actually there was no problem to detect this system. This was the beginning of spin noise spectroscopy. At that moment, we didn't think, we didn't have any hope that it will find some wide application in will be applied in applied physics, so to say, in experimental physics, because we consider this just as a good illustration to fluctuation dissipation theorem, and because we have chosen the object very specially, and if the method is applied to a single system, it's not very valuable. And indeed, for 20 years after that, this experiment wasn't attract much attention, and only at the beginning of this century, when the spin noise spectroscopy was successfully applied to semiconductor systems, and it was applied not only due to just long accumulation time, it was also took place, but one more essential change in experimental technique was a replacement of sweeping spectrum analyzer that was used in our experiment also by Fourier transform spectrum analyzer. And after this, the sensitivity of measurements was increased by more than 2 orders of magnitude, and then the spin noise spectroscopy started to be applied very widely, both in atomic systems and in semiconductor physics. Just to mention the main property of the spin noise spectroscopy, that the experimental setup or spectrometer, spin noise spectrometer, is very simple, very simple. There is nothing but the only thing that the sample is placed in a transverse magnetic field in a tightly focused light beam, properly tuned, then balance detector, and then Fourier transform spectrum analyzer. So the system is very, very simple, and the only heart of the system is a Fourier transform spectrum analyzer, because it makes the main job. It's a huge job, but when you have spectrum analyzer, it is done, and it's easy to use this system. There is no problem, no special knowledge or some sophisticated methods. To compare with usual, so the spin noise spectroscopy can be considered as a sort of magnetic resonance spectroscopy, but as compared to conventional magnetic resonance spectroscopy. First of all, it's non-perturbative, because when the probe light propagates in the region of transparency of the system, it doesn't disturb the system. It's a non-perturbative method. It's very essential, especially in semiconductor physics. Then in conventional spectroscopy, we are tied to, we are restricted by a single frequency at which we observe the resonance signal, and correspondingly for a given G factor, we are restricted to a certain magnetic field. In spin noise spectroscopy, there is no oscillator, no chosen selected frequency. All frequencies are equivalent. We just change magnetic field and just listen. We can say that we just listen to the system, and we hear some sound at some frequency, or detect some signal, and we measure its frequency, its width, its spectrum. This is resonance. So we do not have, we may make measurements in a wide range of magnetic field independent of the frequency. And one more feature of spin noise spectroscopy, which differs it from conventional magnetic resonance spectroscopy, is that in conventional EPR spectroscopy, the system should be polarized. It means that there should be a population difference between two magnetic sublevels. In spin noise spectroscopy, there shouldn't be any difference. The populations may be the same, and so the measurements may be performed at high temperatures or in small magnetic fields. It doesn't matter. And just very briefly, I must say some specific properties of spin noise spectroscopy. If we look at this spectroscopy from optical side, that since it's not a spectroscopy of response, it's something different from the optics, because it shows some properties which are more typical for nonlinear optics. For instance, I told that it's very profitable to tightly focus the laser beam. And the main contribution to the choid is made by this focal point. And if we move this focal point over the sample, we can make a sort of 3D tomography. Which is impossible for linear optics. So, and this tomography was realized based on spin noise spectroscopy. Another example, I will develop on it, is that it's possible to make a sort of pump-prop spectroscopy, because the spot illuminated by one beam can be found by another probe beam without any. Usually you can do such experiment if the pump beam makes some changes optical properties of this spot. But here, just on the basis of statistical properties of the noise, we can perform a sort of pump-prop spectroscopy. Okay, then one very also a sort of effects which is more typical for nonlinear optics. Using spin noise spectroscopy, we can distinguish in homogeneously broadened lines from homogeneously broadened light. Usually, linear optics doesn't allow to do this, and it's very interesting. In the upper part, I just show a line, and on the right side, the Faraday rotation. And it's the same whether the line is broadened homogeneously or inhomogeneously, it doesn't matter. But if the line fluctuates, if the line is broadened homogeneously, it will fluctuate as a whole. And therefore, it just, we can say that it just is multiplied by a time-dependent factor. And so, naturally, in the center of the line, where the Faraday rotation itself is zero, there will be no Faraday radiation noise. And as is shown in the left picture, the optical spectrum of spin noise power will have a dip in the center of the line. But if the line is broadened inhomogeneously, all the packets of this line are fluctuating independently, then there will be nothing of the kind, and the greatest signal, the greatest spin noise power will be observed in the center of the line, where the Faraday radiation itself is zero. And it's very interesting how the optical spectrum of spin noise power evolves with decreasing homogeneous line widths. The peak, the dip in the center disappears, and then in the center, the spin noise power increases and increases as the homogeneous line width becomes smaller and smaller. And this factor of gain, or this factor of amplification of this spin noise power is described by the ratio of inhomogeneous widths to homogeneous widths. And it may reach many orders of magnitude. And this is what has very much to do with application of spin noise spectroscopy to rare earth ions. Now we just come to optical properties of rare earth ions. Everyone knows that there are two kinds of transitions for ions in crystals and in solids. The interconfigurational FF transitions, they are parity forbidden, they are relatively, the transitions are narrow and relatively weak, and very strong, allowed FD interconfigurational transition, which are characterized by broad, homogeneously broadened bands. And of course, at the beginning, when we thought about application of spin noise spectroscopy to rare earth ions, we considered as the best candidates. We considered such ions as divalent thulium or dysprosium or europium, something like that, which are characterized by very strong magneto-optical effects, magneto-optical activity. But these transitions are broadened homogeneously. And but all our attempts and all our estimates have shown that we have no chance to apply spin noise spectroscopy based on this transition. And then we turn our attention to FF transition. They are narrow. The width of FF transition usually lies in the range of from 1 to 10 gigahertz, something like that. But homogeneous line width of this transition lies in the range of lie in the range of kilohertz, and even narrow they can be. And so the factor, the gain factor I told about above, can reach 6 or 7 orders of magnitude. And this was the idea, and we immediately applied our method to rare earth activated crystals in the region of FF transition, and we immediately obtained the result. These are our first experiments. They are. I just don't see the laser. Okay. So we make this measurement like this. We make, and in some fixed magnetic field, we detect the spectrum of spin noise, then we change magnetic field, make measurements in other magnetic field, and then depict it in this color map format, and we obtain this picture. And so they were detected with no problem. It was our victory. We were proud of it. And one more, or some other advantages of this technique is that the measurements are made in a relatively low magnetic field. So the magnetic field can be created by external permanent magnet, and by rotating the external outside the cryostat, by rotating this permanent magnet, we can rotate magnetic field on the sample, and in this way we can measure, we can obtain orientational dependencies of magnetic resonance spectra. We did it just to demonstrate this opportunity. We did it for calcium fluoride with neodymium ions, and we obtained the picture like that. It was very interesting for us. In addition, because we have just analyzing this picture, we understood that frequency in each field, we obtain a panoramic spectrum of magnetic resonance spectrum in contrast to conventional spectroscopy when we are tied to some frequency. And the frequency here, we observed resonance on tetragonal tetragonal centers. There are 3 groups of these centers, and we have found that there are invariants, that the frequency of the transition are related to magnetization of this group of center. And since the total magnetization in cubic crystal in high temperature limit should be isotropic, there arises some invariance, and we published a special paper, but I will dwell upon it. And now I would say the most interesting thing was the following. So the Faraday rotation, the spin noise spectroscopy is based on polarization measurements. It measures noise of Faraday rotation. We know that to measure Faraday rotation in optically anisotropic crystals are very difficult. I would say impossible. Indeed, the polarization during propagation along in an anisotropic crystal, the polarization changes. Usually, this picture is depicted by precession of quasi-spin vector on Poincare sphere, and when we apply, along with strong linear birefringent, we want to detect a small gyrotropy. It means that to the effective field created by linear anisotropy, we just add a small orthogonal field related to gyrotropy, and we just rotate the total field, and nothing changes. I just try to explain why we cannot detect Faraday rotation in strongly birefringent systems. I think that everyone knows that it's the case. And we thought that if we cannot measure Faraday rotation, we cannot measure Faraday rotation noise. It seemed to be natural, but it's not the case. And we have shown that birefringence doesn't prevent measuring Faraday rotation noise at all. It's a mathematical result, but I can explain it briefly in the following way. If we no matter what is, so when the polarized light enters the anisotropic medium, and the output, we have also polarized light, but of arbitrary polarization. We don't know polarization. But what's important that it doesn't fluctuate. It's a fixed polarization. Polarization of this light is fixed. But if the system exhibits some gyration of the system, exhibits some fluctuations, this polarized light, no matter what is its polarization, will fluctuate. And these fluctuations do not depend on whether the system is isotropic or anisotropic. It's a very interesting result, and we applied to this method of spin noise spectroscopy to anisotropic crystals, and we immediately obtained the signals of the same magnitude. it's very, in our opinion, it was a very interesting result, because usually when we were asked, can you apply your method to this system? First of all, I asked, is it isotropic or anisotropic? It's anisotropic. Oh, no, I'm afraid not. But now we see that there is no problem to apply it to any anisotropic system. And it's just 2 weeks ago we published this result in Physical Review Letters. The last thing, at the beginning of this talk, I told that the most favorable geometry is when the light beam propagates across the applied magnetic field. And when the light beam propagates along magnetic field, there is no signal oscillating at Larmor frequency will be observed. But it's not the case if we deal with anisotropic centers. And I just give you, better to say the words that if we have some anisotropic center arbitrarily oriented in magnetic field, then it feels different components of magnetic field with different, so to say, sensitivity along the line, along the axis of the G tensor with greatest value, it feels this component better than other components. And as a result, the field that feels the center is tilted with respect to external field. So in laboratory coordinate system, the geometry is Faraday geometry, because the magnetic field is along the light propagation. But for anisotropic center, it's not exactly Faraday geometry, so it's partly Fock geometry, and we observe, and we can observe in any geometry, in Faraday geometry and Fock geometry, we can observe this resonance. And on the right, we show that it doesn't depend, that the intensity of the lines are isotropic, no matter what is the geometry. And there is also one more example. We rotated magnetic field, and here the magnetic field changes from Faraday geometry to Fock geometry, and the signals remain the same. Okay, so actually this is, I just was hurried to present this result, and they are just illustration of possibilities of the spin noise spectroscopy. It wasn't really applied so far for real scientific research, but I hope that in the nearest future it will be evaluated properly and will find application to rare earth activated crystals and glasses. Thank you very much.
Veleriy, thank you. Thank you very much for a very interesting talk. Do you hear me? Do you hear me?
Yes, yes, I hear, yes.
Yes, and I must say that Professor Zapasskiy, who worked in the laboratory of Pyotr Petrovich Feofilov, was awarded by the state prize in 2020 for the invention and development of the method of the spin noise. Thank you very much once more. And now, please, your questions. Are there any questions? Maybe I'll ask the first question. Veleriy, do you hear me?
Yes, yes, there is one question I see.
Tell us, please, what could be the reason that you did not observe these deep in homogeneously broadened lines of FD transitions? What could be the reason?
What's the reason that they couldn't be used in spin noise spectroscopy, you mean?
Yes.
You see, the answer is very simple. I can say that in atomic system, we usually deal with spin density of around 10 to the 12 per cubic centimeter. In semiconductor system, they are 10 to 16, approximately 15, 16. In rare earth activated crystals, these concentrations are 10 to the 19. Usually, and correspondingly, since the spin noise power scales as inverse square root of the number of particles, it just the sensitivity appears to be low. The signal is low. So Faraday rotation to a single ion is very small.
I see. Okay, thank you. More questions, please.
Yes, I have a question. Thank you very much for a very interesting talk. I have a question about why all people in the world using, for example, not for example, but EPR spectroscopy instead of spin noise spectroscopy. As I understand from answer to Marina Popova, it is due to you need very clear crystals, yes?
Very
good, very clear crystals without low concentration of the magnetic centers, no? Because you said before that you can't measure high concentrated systems. Like 10 to the 15, 10 to the
But
19.
it's not, when I say that concentration lies in the range of 10 to the 19, it doesn't mean that concentration, it's concentration of 0.1%. It's not.
Yeah. So but why people using EPR spectroscopy if we have such a good method as spin noise spectroscopy?
You see, it's on the one hand it's good, on the other hand it's not so good, because of course when you detect a regular signal, you can do it with much higher sensitivity. That's right. Then, but there are many advantages. For instance, when we in these experiments with neodymium or ytterbium ions, we just in optics we selected a resonance transition, and when we observe the magnetic resonance spectrum, we are absolutely sure that these are these ions. In EPR spectroscopy, we see all
yes. I understand you. Thank you.
Yes,
thank you very much.
They are different.
Thank you. And some more questions. So let us thank the speaker.
One more question.
Okay.
One more question, please.
Are there any prospects for using this interesting technique for the films? I mean, Kerr geometry. Actually, for measurement of Kerr rotation, quite sensitive system can be used.
You mean Kerr rotation in reflection? In reflection. Yes, it's possible, and it's used. We made such experiments, though they were made on quantum well systems, but they were in reflected, and it works.
Okay, maybe afterwards it will be interesting to discuss with you. Thank you.
Yes.
Okay, no more questions. Let us thank the speaker.
Thank you very much.